Welcome back to the deep dive. Today, we aren't just talking about, another AI model update or some new chatbot.
No.
We are looking at the plumbing, the actual architecture of how intelligence is built. And honestly, the current architecture it's kind of a mess.
It is a mess. I mean, it's effective, but
Yeah,
a mess.
right. Because for the last decade, the recipe for AI has been pretty crude. You just take all the data you can find, emails, photos, financial records, suck it all up like a vacuum cleaner, and dump it into one massive centralized server farm. A data lake, if you want to use the polite term.
Or a data swamp, depending on who you ask.
Exactly. But here is the problem, and this is the real hook for today. The most valuable data in the world, the stuff that could actually cure diseases or predict financial crashes, it's the stuff that you cannot move. It's locked in these silos. Hospitals can't just email patient records to Google.
Oh, wait.
Banks can't just upload transaction ledgers to a public cloud.
And that is the central paradox of modern AI. To get smarter, models need access to all that sensitive data. But to stay secure and, compliant, that data has to stay hidden.
So we're stuck.
For a long time, yeah, we've been stuck. We have dumb models in secure places or smart models in insecure places.
Which brings us to the question we are answering today. How do you train a model without ever actually seeing the data? It sounds like a magic trick.
It does, but it's actually just very clever math. We're deep diving into two technologies that are solving this: federated learning.
And encrypted AI agents.
Right. And just to set the stakes here, this isn't just about privacy. This is about rewriting the economic rules of the internet.
Okay, let's start with that first piece of the puzzle then. Federated learning. The source material had this great tagline, train locally, learn globally, which sounds great, but let's be real, what does that actually look like?
So flip the traditional model completely upside down. In the old world, you bring the data to the code. You upload your photos to the server trains the model. In federated learning, you bring the code to the data.
So the model travels to me.
Yes. Let's say we're trying to build a predictive text keyboard for smartphones. Instead of uploading everything you type to a central server, which is, a privacy nightmare.
A total nightmare.
The central server sends a generic, sort of rookie version of the AI down to your phone.
Okay, so now my phone has this rookie AI.
Right. And for the next few days, that AI just lives on your phone. It watches what you type. It learns your slang, your typos, the weird emojis you use. And it trains itself right there on your device's processor using your local data.
Wait, hold on. If my phone is doing the heavy lifting of training an AI, isn't that going to absolutely torch my battery? Training models is computationally expensive.
That is a legitimate engineering hurdle, a big one. You can't just run this anytime.
Right.
Usually these protocols are set to only run when the device is, plugged in, connected to Wi-Fi, and idle.
So like at 3 in the morning?
3 in the morning, yeah. But even then, there's a challenge with what we call stragglers.
Stragglers.
Yeah. Imagine doing this across 1 million phones.
Yeah.
Some are the latest flagship models. Others are like 5 years old with cracked screens. The central system has to coordinate all of this, waiting for the slow devices to catch up without holding back the fast ones. It's a logistical nightmare.
Okay, so let's say my phone manages to do the training at 3 a.m. It's learned my specific typing habits. Now what? Does it send the data back?
No. And this is the most critical definition we need to get right today.
Okay.
It does not send data. It sends a gradient update.
Gradient update. We hear this term thrown around in ML papers all the time. Let's actually unpack it. What physically is getting sent?
Okay, so think of the AI model as a map of a mountain range. And the goal is to get to the lowest point, the point of lowest error.
Got it.
Your local data tells the model, hey, to get better, you need to take 3 steps fast. That direction, that vector pointing towards better, is the gradient.
So I'm not sending the text I typed. I'm sending a mathematical vector that says, adjust the weights in this direction to make the model less wrong.
Precisely. It's a directional arrow. Your phone sends that arrow back to the central server.
And the
server collects millions of these arrows from millions of phones. It averages them out, this is called federated averaging, and uses that average to update the global master model.
So the master model gets smarter generally based on everyone's specific experiences, but it never actually saw the raw data.
That's the promise.
Yeah.
Collaboration without centralization.
Okay, so that sounds perfect. We solved privacy, pack it up, show's over.
I wish it were that simple.
I knew it. There's always a catch.
The catch is that
I know.
Well, we underestimated the cleverness of attackers. We assumed that because you're only sending a gradient,
Just a vector of numbers.
right, just a vector of numbers, that the raw data was safe. But researchers started looking at these gradients and realized they contain a lot more information than we thought.
You're talking about gradient inversion attacks, right?
Yes. This is the stuff that keeps security engineers up at night. It turns out, if I have access to the model and I see the specific gradient update you sent,
Yeah.
I can reverse engineer the data that created it.
How is that even possible? It's just an adjustment. It's like telling a chef, add more salt. You shouldn't be able to figure out the whole recipe from that.
Well, if the gradient is high-dimensional enough, and modern models have billions of parameters, that add salt instruction is actually incredibly specific.
Wow.
There's a famous paper where researchers took a gradient update from an image recognition model, and just by analyzing the math, they reconstructed the original image.
Like the actual photo.
Almost pixel perfect. They reconstructed a face from the gradient.
That is terrifying. So I think I'm safe because I never uploaded my photo, but I sent a math update that basically allowed the server to paint a portrait of me anyway.
Exactly. So federated learning alone, it's better than centralization, but it is not a silver bullet.
No.
You are still exposing information, just in a derived form.
So we need another layer. We need to blind the central server so it can't even see the gradients.
And enter our second technology, encrypted AI agents.
Now, when we say encrypted, I think most people assume standard encryption. Like, I lock a file with a password, I send it to you, you unlock it, but that doesn't work here, right?
No, because the central server needs to use the data. It needs to average those gradients together.
Right.
If they're locked inside a digital safe, the server can't do the math. Standard encryption makes data useless for computation.
So we need a way to do math on the safe while it's still locked.
And this is where we get into the heavy stuff, homomorphic encryption.
That is a $10 word, homomorphic.
It comes from Greek, same structure.
Yeah.
It allows you to perform calculations on encrypted data, and when you eventually decrypt the result, it's the same as if you had done the math on the raw numbers.
That sounds impossible. That's like solving a Rubik's Cube while it's inside a steel box.
That's actually not a bad analogy, but let's go with the glove box analogy because I think it captures the difficulty better.
Okay, glove box.
Imagine a high-security biolab. You have a sealed glove box with thick tinted glass. You can stick your hands into those rubber gloves and manipulate the test tubes inside.
Okay, so I can move things around, I can mix chemicals.
Right, you can do the work. But the glass is so heavily tinted, you can't see what color the chemicals are, you can't read the labels. You are performing the experiment blind.
So the central server is the person in the gloves. It's grabbing all these encrypted gradients, mixing them together, doing the aggregation.
Yes.
But it never actually sees the numbers.
Correct. It performs the addition and averaging on the ciphertext, the scrambled code. It produces a result that is also encrypted. It sends that back to the phones, and only the phones have the key to unlock it and see the new, smarter model.
That is mind-bending. But wait, if we're doing math inside a glove box, isn't that clumsy?
Clumsy is an understatement. This is the big trade-off that people gloss over. Homomorphic encryption is incredibly computationally expensive.
How expensive?
We call it the overhead. Doing math on encrypted data can be thousands of times slower than doing it on plain data.
Thousands.
Easily. It's getting better. Hardware acceleration is helping. But it creates a massive computational tax. You're trading speed for absolute privacy.
So this isn't something we're going to use for everything. You wouldn't use this to recommend me a YouTube video.
Probably not.
Well,
for the high-stakes stuff, absolutely.
Let's ground this then. We've got the theory. Federated learning keeps data local. Encryption keeps the update safe. Where does this actually hit the road? The source mentioned a specific case with heart disease research that I thought was really compelling.
Yeah, this is the perfect example of where that computational tax is worth paying.
So walk us through it.
Okay, imagine a scenario. You have 3 different hospitals: Rural Clinic A, City Hospital B, and Research Center C.
Okay.
They all want to train an AI to detect a very rare heart condition, hypertrophic cardiomyopathy from ECG scans.
And since it's rare, no single hospital has enough patients to train a good model. Clinic A maybe has 2 cases. Hospital B has 20.
Right. If they rely only on their own data, the model fails. It's just not smart enough. In the old world, they would try to sign these huge data sharing agreements to pool their records.
Which takes 5 years of lawyers arguing, high-pay compliance checks, and usually just falls apart.
Exactly. So the data stays in silos, and the model never gets built. Patients die because the diagnostic tool doesn't exist.
Grim. So how does this new stack fix it?
Step 1. Setup. All three hospitals agree on a model architecture. Let's say a standard convolutional neural network. They install it locally behind their own firewalls.
So the model goes to the data.
Step 2. Local training. Rural Clinic A runs the model on their few patients. City Hospital B runs it on their many patients. The model learns locally, oh, this spike in the ECG means danger.
Step 3. The gradient.
Yes, but an encrypted gradient. Each hospital generates that mathematical update vector. Then they wrap it in homomorphic encryption. They put it in the glove box.
And they send it to whom?
An aggregator. This could be a cloud server run by a university or a tech company. But here is the beauty. The aggregator is blind.
Right.
It receives 3 locked boxes. It uses homomorphic addition to combine the contents of the boxes without opening them.
So it merges the wisdom of the rural clinic and the city hospital?
It creates a new aggregated encrypted update and sends it back. The hospitals decrypt it, update their local models, and suddenly the doctor in the rural clinic has an AI that is as smart as if it had seen every patient in the city.
But not a single patient record ever left the building.
Not one.
That's a game changer. It's collaboration without compromise.
It completely removes the trust barrier. You don't have to trust the other hospital. You don't have to trust the cloud provider. You just have to trust the math.
And I imagine this applies to way more than just healthcare.
Oh, yeah. Financial fraud is the other big one. Banks want to stop money laundering, but they can't show their transaction data to competitors.
Of course not.
With this, they could jointly train a money laundering detector that learns from patterns across all banks without any bank seeing another bank's specific client data.
So if this works, and it seems like it is working despite the computational cost, what does this do to the big data business model?
That is the trillion-dollar question.
Because for the last 20 years, the strategy for tech giants has been build a moat, hoard as much data as possible because he who has the most data wins.
Right. Data was the new oil. You drilled for it, you stored it, you refined it. But if federated learning and encrypted agents become the standard, the value of hoarding data drops to 0.
Explain that.
Well, if I can trade a state-of-the-art model by tapping into data that lives on your phone and her laptop and his server without ever owning that data, then I don't need a massive data center. I don't need to track you across the web. The competitive advantage shifts from who owns the data to who has the best orchestration.
Who can build the best alliance?
Exactly. It democratizes intelligence. You could have a consortium of small credit unions building a fraud detection system that rivals J.P. Morgan just by federating their data.
It feels like a return to the decentralized promise of the early internet.
In a way, yes.
Yeah.
It allows us to have the benefits of big AI, the superintelligence, the predictive power, without the dystopian surveillance state that usually comes with it.
Although I have to play devil's advocate one last time. If the data stays on my device, does that mean I, as the user, have more power? Or does it just mean the tech companies are offloading their server costs onto my electricity bill?
A little bit of column A, a little bit of column B.
I thought so.
Yes, you are paying the electricity for the training, but you are also retaining sovereignty. You can, in theory, opt out. You can unplug. In a centralized world, once they have your data, they have it forever. In a federated world, if you stop participating, you stop contributing.
It's a fascinating shift. We're moving from data as a resource to be extracted to data as a skill to be practiced locally.
That's a beautiful way to put it.
So to wrap this up, for everyone listening who is maybe feeling a bit overwhelmed by the encryption talk, what is the one thing they need to take away from this?
The takeaway is that privacy and progress are no longer enemies.
Yeah.
We used to think we had to choose. Do you want a smart world or do you want a private world?
Right.
These technologies, federated learning and homomorphic encryption, prove that's a false dichotomy. We can have both.
We can have the cake, eat it, and nobody has to know the recipe.
Close enough?
I want to leave the listeners with a final thought to mull over. We talked about how this disrupts business, but think about what this does to liability. If an AI makes a mistake, but that AI was trained by 1 million anonymous users and aggregated by a blind server, who is responsible?
That is a legal nightmare that I am glad I don't have to solve today. But it's coming.
The era of the blind agent is just starting. Thanks for unpacking this with me. It was a heavy one, but I think we got there.
My pleasure. It's complex, but it's the future.
Stay curious, everyone. We'll see you in the next deep dive.